In September 2025, Chinese scientists unveiled the world's first 6G chip, achieving a staggering transmission speed of 100 gigabits per second. But this seemingly straightforward technological breakthrough masks something far more significant. Behind the scenes, an intense global battle for digital supremacy is quietly unfolding. China has already built 4.19 million 5G base stations, accounting for over 60% of the world's total, and has successfully established 3 6G technical standards within the ITU. Meanwhile, Western nations, including the United States, lag 2 to 3 years behind in their 5G deployment. This raises a critical question: why does a technology that seems distant and futuristic cause such anxiety among the world's most powerful nations, prompting them to pour trillions of dollars into securing control over standard-setting authority? Back in 2019, when countries around the globe were announcing their 5G commercial launches, most people overlooked one crucial metric: base station density. That year, China Mobile made a bold decision. They would build out their 5G base station network at any cost. Critics at the time questioned whether this great leap forward approach to investment made any sense. After all, a single 5G base station costs hundreds of thousands of dollars to build, yet covers only 1/3 the area of a 4G base station. But by the end of 2023, the power of this strategy became crystal clear. US statistics from 2022 showed the country had only about 140,000 5G base stations nationwide. Germany had even fewer, with less than 30,000. In stark contrast, China had already built over 4 million 5G base stations during the same period. This tenfold gap represents far more than just a numbers game. Every single base station represents control over data flow. When your phone connects to a network, the signal first reaches the nearest base station, then travels through the core network to its destination. Whoever controls the base station network controls the first gateway to data. More critically, the technical standards and protocols embedded in these base stations directly determine the rules of the entire network ecosystem. Huawei played a pivotal role in this base station race. In 2020, the United States began restricting the use of Huawei 5G equipment in allied countries, citing national security threats. But what really made America anxious was the fact that Huawei base station equipment had already penetrated more than 30% of the global market. This meant that over 1/3 of the world's 5G networks were running on hardware made in China. The United Kingdom initially allowed Huawei to participate in its 5G build-out, but under pressure from the United States, announced in July 2020 that it would completely remove Huawei equipment. The cost of this decision was staggering. The UK's 5G deployment timeline was pushed back 2 to 3 years, with additional costs exceeding £7 billion. The deeper impact lies in the shift of standard-setting power. After China achieved overwhelming dominance in 5G base station construction, the influence of its technical proposals and standard submissions within the International Telecommunication Union, or ITU, surged dramatically. In 2023, Chinese companies accounted for 37% of all 5G-related patent applications submitted to the ITU, far exceeding America's 16% and the European Union's 8%. This advantage laid the foundation for the 6G competition. The country with the world's largest 5G network gains the richest real-world deployment experience, and this experience translates directly into leverage in setting 6G standards. The infrastructure wars of today are shaping the technological landscape of tomorrow, and China has positioned itself at the forefront of this transformation. In February 2024, the International Telecommunication Union's headquarters in Geneva hosted a special meeting. Communications experts from 42 countries gathered to discuss a question that seemed technical but carried enormous political weight: how should 6G technical standards be established? The Chinese delegation submitted a 147-page technical proposal covering the core architecture design for 6G. The document's thickness impressed the experts in attendance, but what truly stunned them was its technical depth. China didn't just propose a spectrum allocation plan. The proposal detailed a comprehensive architecture for integrating 6G networks with artificial intelligence and satellite communications. 3 months later, the ITU officially approved 3 6G technical standards submitted by China. These were the first batch of approved standards in the 6G standardization process, meaning China had secured a first-mover advantage in the fundamental architecture of future 6G networks. America's response came swiftly. In February 2024, the United States joined with Australia, Canada, the United Kingdom, and 7 other allied nations to release the 6G Joint Declaration, emphasizing support for open, free, globally interoperable, reliable, resilient, and secure connectivity. On the surface, this was a technical manifesto, In reality, it was a counterbalance to China's dominant position in 6G standards. So what's really at the heart of this standards battle? The answer lies in control over network architecture. Traditional communication networks use a centralized architecture, where core equipment controls the entire network's operation. But 6G proposes a distributed concept, pushing computing power down to the network edge. This architectural shift appears to be a technical optimization, but it actually reconstructs the distribution mechanism of data control rights. China's 6G standard proposal particularly emphasizes the concept of computing network integration. Simply put, this means embedding computing capabilities directly into network infrastructure, giving the network itself intelligent decision-making abilities. The advantages of this design are significant. Data processing latency drops to the millisecond level, and network efficiency increases dozens of times over. But this has also sparked concerns among Western nations. Under a computing network integrated architecture, network infrastructure is no longer just a simple data pipeline. It becomes an intelligent brain with data analysis and decision-making capabilities. Whoever controls this brain controls the processing and flow of data. The European Union, in its 6G strategic white paper released in September 2024, explicitly proposed establishing European-led 6G standards. The 6G technical solution jointly released by Deutsche Telekom and Nokia particularly emphasized the concept of data sovereignty, ensuring that European data is processed on European networks. The consequences of this fragmentation trend are serious. If a unified standard cannot be reached, the world may see multiple parallel 6G network standards, leading to reduced network interoperability and hindering the integration of the global digital economy. More critically, there's the battle over patent positioning. By the end of 2024, Chinese companies had filed 24,000 patents in 6G-related technology fields, accounting for 40.5% of the global total. The United States followed closely behind with 18,000 patents, representing 30%. The European Union lagged relatively behind with only 8. The gap in patent numbers directly affects future licensing fee distribution. If China's 6G patents become industry standards, every 6G device in the world will need to pay licensing fees to Chinese companies. This isn't just about economic benefits. It's about the embodiment of technological discourse power. In January 2025, China's Ministry of Industry and Information Technology released the National Data Infrastructure Construction Plan, clearly stating the goal of completing 6G key technical standardization work by 20. This timing wasn't chosen randomly. It coincides precisely with the ITU's scheduled deadline for finalizing 6G standards. On September 1, 2025, the journal Nature published a paper by Chinese scientists with a highly technical title, Ultra-Wideband On-Chip Photonics for Full-Spectrum Wireless Communications. But the impact of this paper reached far beyond the academic world. The paper described a chip measuring just 11 mm by 1.7 mm, yet capable of covering the entire spectrum from 0.5 to 115 GHz, with data transmission speeds exceeding 100 gigabits per second. Even more remarkable, this chip could complete a 6 GHz frequency adjustment in just 180 microseconds, nearly 1,000 times faster than existing technology. What does this breakthrough actually mean? To understand its importance, we need to first grasp the core challenges of 6G technology. Traditional communication chips can only process signals in specific frequency bands. For example, 5G chips primarily work in the 3.5 GHz and 28 GHz bands. But 6G needs to cover the entire spectrum range from microwave to terahertz, which requires integrating multiple frequency band processing capabilities on a single chip. Previously, this required multiple independent chips working together, which not only increased costs but also introduced signal delay problems. The innovation from Chinese scientists lies in their use of thin-film lithium niobate material, integrating optical and electronic functions on the same chip. Signals are first converted to optical signals for processing, then converted back to electrical signals for output. This optoelectronic integration design not only solves the full spectrum coverage problem, but also dramatically improves processing speed. Huawei's positioning in this field began as early as When the United States imposed chip restrictions on Huawei, most observers believed Huawei's technological development would be severely damaged. But Huawei chose a different path. They engaged in deep cooperation with research institutions like the Chinese Academy of Sciences and Tsinghua University, focusing on next-generation technology development. This technology leapfrogging strategy is now showing results. Although Huawei faced restrictions on 5G chips, in 6G chip technology, China has already moved ahead of the rest of the world by one generation. America's response was swift. Within a week of China's 6G chip breakthrough announcement, the U.S. Department of Commerce added 6G-related terahertz technology to the export control list. At the same time, the U.S. Congress passed the 6G Innovation Act, planning to invest $120 billion over the next 5 years in 6G technology research and development. But this catch-up effort faces structural difficulties. During the 5G era, America adopted a technology outsourcing strategy, relying on Qualcomm for core chips and primarily sourcing base station equipment from Nokia and Ericsson. This model works efficiently in mature technology periods, but becomes rigid during periods of rapid technological iteration. Qualcomm's 6G chip roadmap, released in July 2025, shows that its first 6G chip won't be ready for mass production until 2027, and even then will only cover certain frequency bands, requiring coordination with other chips. In technical specifications, Qualcomm's solution clearly lags behind China's in both transmission speed and spectrum coverage. More importantly, there's a gap in supply chain integration capabilities. Behind China's 6G chip breakthrough lies a complete industrial chain supporting everything from materials to manufacturing to packaging and testing. The thin-film lithium niobate material was provided by the Chinese Academy of Sciences Institute of Optics and Electronics. Chip design was completed by Huawei's HiSilicon team. Manufacturing was achieved on SMIC's 28-nanometer process line. This vertical integration capability allows China to rapidly transform laboratory results into industrialized products. By 2026, base station equipment based on this chip is expected to begin small-scale trial production. Japan and South Korea are also accelerating their catch-up efforts. Samsung announced in August 2025 that it would invest $30 billion to build 6G chip production lines, with a goal of achieving commercial production by 2020. Sony is focusing on 6G chip image sensor technology, hoping to gain an advantage in holographic communications. But individual breakthroughs are unlikely to shake the overall landscape. 6G technology is a complex systems engineering project requiring coordinated development across the entire industrial chain, including chips, base stations, terminals, and applications. The industrial chain advantages China established during the 5G era are now extending into the 6G era. This consolidation of technological leadership also provides powerful confidence for the next phase of market competition. In October 2025, a seemingly ordinary business news item drew global attention. China Mobile and Saudi telecom company signed a 6G cooperation agreement, planning to build the first 6G trial network in Saudi Arabia by 2020. The significance of this agreement far exceeds the commercial cooperation itself. As a technology hub in the Middle East, Saudi Arabia's network choices often influence the technical direction of the entire Arab world. China's success in the Saudi 6G project means gaining an important strategic foothold in the future global 6G market competition. Meanwhile, the United States was also accelerating its global positioning. In September 2025, America announced the formation of the 6G Global Alliance, with initial members including Japan, South Korea, the United Kingdom, Australia, Canada, and 7 other countries. The alliance's goal was clear: to establish a set of 6G standards and industrial chains independent of China's technology system. This competitive landscape fragmentation reflects a deeper change in the 6G era. Technology choices are becoming increasingly politicized. In the 4G and 5G eras, carriers' technology choices were primarily based on cost and performance considerations. Whichever company offered cheaper, better equipment got selected. But in the 6G era, geopolitical factors are starting to dominate. The United States has explicitly required allied countries not to use Chinese 6G equipment. The European Union is also considering similar restrictions. The consequences of this technological polarization are complex. On one hand, it may lead to fragmentation of the global 6G network, creating mutually incompatible technical standards. On the other hand, it's also driving diversified development in technological innovation, avoiding the risks of a single technical path. China's response strategy is technological inclusiveness. In November 2025, China's Ministry of Industry and Information Technology released the 6G International Cooperation Initiative, emphasizing that 6G technology should serve all humanity and opposing technical barriers and standard fragmentation. This initiative gained support from multiple developing countries, including Russia, India, and Brazil. More practical positioning involves seizing application scenarios. China has proposed the 6G city concept, planning to build 6G application demonstration zones in Shenzhen, Shanghai, Beijing, and other cities, focusing on showcasing 6G's application potential in smart manufacturing, autonomous driving, telemedicine, and other fields. Shenzhen's 6G test zone has already taken initial shape. At BYD's Smart Factory, a digital twin system based on the 6G network can monitor the production status of every component in real time, improving production efficiency by 35% compared to traditional factories. At Shenzhen People's Hospital, doctors use the 6G holographic communication system to provide remote surgical guidance for patients thousands of miles away. With a surgical success rate of 90%, the success of these application scenarios provides powerful persuasive power for China's global promotion of 6G technology. After Saudi government officials witnessed the actual effects of Shenzhen's 6G applications, they quickly decided to adopt China's technical solution. America's 6G strategy relies more heavily on technological alliances. The 6G Global Alliance plans to invest $500 billion in 6G technology research and development and infrastructure construction. But this model faces problems of high coordination costs and low decision-making efficiency. Within the alliance, there are disagreements about technical paths and standard choices. Japan leans toward millimeter wave technology. The European Union prefers sub-6 GHz solutions. America wants to emphasize both. The window of opportunity is rapidly narrowing. The ITU is scheduled to complete the final version of 6G technical standards in 2026, begin small-scale commercial trials in 2027, and achieve full commercial deployment by 2030. From a technical readiness perspective, China is clearly in the lead. But whether this technological advantage can be converted into market advantage depends on the global game being played out over these final 5 years. One key variable is cost control. Although 6G technology is advanced, if construction and operating costs are too high, it will affect commercial promotion. China's cost control experience accumulated during 5G construction may become an important advantage in the 6G era. By estimate, the cost for China to build an equivalently sized 6G network is 30 to 40% lower than their European and American counterparts. Another variable is the maturity of the application ecosystem. The true value of 6G lies in supporting new business models and application scenarios. Whoever can establish a mature 6G application ecosystem first will take the initiative in this competition. China's massive domestic market and vibrant internet innovation ecosystem provide natural advantages for rapid iteration of 6G applications. The 6G battle is essentially a microcosm of the reconstruction of international order in the digital age. From the numbers race in 5G base stations, to the rules game in 6G standards, and then to the breakthrough competition in chip technology, this war without gunpowder determines the distribution of discourse power in the global digital economy for the next decade. Technology leaders will not only gain economic benefits, but will also master the power to set the rules of the digital world. At this critical historical juncture, every technological choice has the potential to rewrite the landscape of global competition. The question isn't just who builds the fastest network or creates the most advanced chip. It's about who shapes the future, who writes the rules, and ultimately, who holds the keys to the next era of human connectivity. The race has begun, and the stakes have never been higher.